Hi, welcome to demonstrating an end-to-end pipeline for machine learning and deep learning leveraging GPUs. So obviously GTC here. Okay, I'm Moses. I'm the founder and CTO of ClearML. A bit about me and the company. I started 15 years ago with machine learning back in the day when it was mostly about kernel methods, SVMs, etc. I'm a professional PhD failure, which means I never actually graduated, to the dismay of my mother. I went and started a company. When we started, so we just recently rebranded as ClearML before Allegro AI. When we started this company, we set to actually solve all the issues that we had when we were building machine learning and deep learning infrastructure, which essentially can be boiled down to automation and how to make automation as part of the development process without constantly writing infrastructure code and changing the data science code, right? So the idea is to do as little as possible in terms of integration, but on the other side, get the full automation, visibility, and pipelines that we can expect from MLOPS framework. So with that in mind, we created the open source ClearML framework, which it does exactly that. It automates this entire process, and it allows you to constantly be at the stage where you're writing code and deploying it and automating it without the need to change the code base, your own code base, or adhere to any specific infrastructure when it comes to the integration process. And in this session, I'll demonstrate how actually to accomplish that with a few examples and the help of NVIDIA TLT as kind of a real-world example of automation end-to-end pipeline. Okay, let's get started with why is it actually hard. So the reason why it's actually hard, it's because as software engineers, we expect that everything is kind of a linear process, right? So what we have today is better than what we had before, and we have some goals and some bugs, and we fix them, and we go in a straight line. But when we think about machine learning and deep learning, things are a bit more complicated, right? So we have different challenges, right? So we have the code itself, but we also have the data coupled with the code somehow, and we have the parameters that we want to use in order to train the model based on the specific data that we are using. And then at the end, we have the model that is kind of the output, but the process of creating that model, we can think of it as kind of a compilation, right? And that compilation process, that training process of the model is not quick. Like best case scenario, a few hours, worst case scenario, a few days. It's very hard to understand if something went wrong when the process itself takes a few days, right? So we have to move from manually running things and debugging them to a more of abstract notion where we write something, make sure that it doesn't crash, but then we spin multiple instances with different variations, so configurations or data and whatnot, making sure that we basically test as much as possible at the same time. So when we do have a success, we didn't actually spend time waiting for something to happen when there's nothing into it, right? So that's kind of the idea. So how usually things are done, right? So when we think about pipelines, or in other words, automation, we think about a very straightforward process, right? You finish your research, right? So you have some code and it's working. You somehow connect it with some underlying pre-processing and post-processing of your process. You make sure you have kind of a nice interface so you can move data from one to the other. You fix some bugs, you package everything, and you somehow deploy it. And obviously, when you change the code, you have to redo most of those steps again. And obviously, the challenge is, I don't want to do that, right? I want to make sure that when I have something that is working, I can immediately test it on real-world data, right? It's not feasible to constantly use an entire data set that is probably larger than the amount of storage that I have on my machine, or that every time I need to wait several hours, again, best case scenario, to make sure that it works. I want to make sure that it doesn't crash, so meaning the code is working, and then test it while I'm working on the next iteration of my code base, right? And that is obviously the challenge here. So let's try to separate it into kind of 3 very basic stages that we can think of, so we make things more concrete, right? So what are those steps? So the first is obviously getting data. So usually that actually involves some code, right? So getting data can be fetching data from databases in production. It can be some sort of feature extraction. It can be normalizing or conforming the data into a format that we can later use, right? So NumPy arrays, Parquet files, CSV files, whatnot. So that is the first step, and we have to end up with a data set that is, first of all, immutable, right? So we can later reproduce a model, understand that if something didn't actually work for us, then we can actually rerun the same code and try to debug it. But also for visibility, right? So we understand that we have more data, we can replicate this entire process and only switch one data source to another and then rerun the entire process. So what exactly is the next step in this process? So the next step in the process itself is obviously the training session itself. So when we think about the training session itself, we think about the taking the code and that does the training, combining it with the data that we just did in the previous step, running that for several hours, days, etc., ending up with a model. And then the last part is obviously taking that model and actually using it, right? So pushing it into production, somehow connecting one to the other, then obviously having the ability to trace back if a model had a drift, what exactly did we do in order to reproduce the model, and then obviously add some more data or mess around with parameters. So let's rethink this process of pipelines, right? So let's try to address the problem only instead of top-down, bottom-up, right? So bottom-up means, okay, so the first challenge is, okay, we just need to somehow package the code itself. The next is we should have somewhere else to store the configurations and parameters, right? If we are storing them inside the Git repository, it means that we're not separating one from the other. It means that we cannot change them, right? We cannot have every time we want to change the parameters themselves, have another commit in the code base itself, right? The code base is still kind of linear, and we want to parallelize the training sessions, right? So it cannot be there. We have to store it somewhere else. And then we have to store the data as well, right? So again, storing the data cannot be just pointing to production database, and that's obviously not a good idea, but the issue here is reproducibility. Those databases are constantly changing, and we have to make sure that we have a way to store the data in an immutable way that is also accessible from everywhere that we're training the code, right? So we have to connect it with some sort of a storage solution, but also introduce a very easy to use API. I don't want to mess around with a lot of code just to get the data on my machine to debug it, or on another machine. I don't want to have to set up very sophisticated DevOps solution just in order to get some data, right? It should be part of my code base that just tells the system, just fetch me the data with some parameters saying this is the data that I need. Okay, so that's kind of the new paradigm here. With that in mind, let me just try to explain how ClearML basically solves that entire process. So again, ClearML is the platform that we developed. It's fully open source, really end-to-end. From the client side to the server side, you can either install everything yourselves or use our free tier if you don't want to set up your own control plane server. What I'll be talking about here is basically the first step. So the first step is obviously creating a job itself. And the idea here is that when we think about creating a job, it should not be like configuring a YAML file. It should be transparent and it should be automatic, right? Because I have a machine that I'm running my code on, and that machine, it already has the environment that I need in order to reproduce my code, right? I worked hard to make sure that that happened. There is no need to try to redo this process, right? So the idea is that while I'm running the code itself, when I'm developing it, automatically I'm creating those job templates. And that is part of the auto magic of ClearML. While I'm running and writing the code itself on my machine, actually debugging the code, I'm actually creating those job templates in the control plane, in the server itself. And this is basically the creation, moving from the code execution into the job template. And that is done automatically for us. Now that job template actually stores both the definition of the environment, so think Git repository link and uncommitted changes and argparse arguments and configuration file, etc. But it also later stores the metrics that we're producing and artifacts. We'll get into that later. So a job template is the definition, and when we replicate that job definition, we can edit it. So again, think of it as kind of a configuration file on steroids, only everything is done for us. So the creation is done for us. We can still edit this job template, add new parameters. So for example, changing the command line arguments, etc. Once we're done with that, we can push that job template into the orchestration solution. Think of it as basically taking the unique ID of that job template and then pushing it into an execution list. And that becomes, from a template, that becomes a real job. Now, right now, an agent running on a machine will pull that job from the execution queue, set up the entire environment, and spin the code and monitor this entire process. So we're moving from the creation of the job from code to the creation of a job template to the creation of a job in a seamless way. And the agent itself, that's the part that is responsible for actually spinning the code. And we'll touch that. We'll touch the agent in a second. The idea is that the agent itself can sit either on bare metal, on the cloud, as part of your Kubernetes cluster, or any other combination, right? So the agent is just a piece of code that replicates and restores that environment and spins the code for us. And it was built in a mindset that means that you should be able to start small and grow with any combination that you like. So how does it all fit together? So what we'll do in the next few slides is we'll go over this entire process from integrating the code with the ClearML platform. And then we'll take the NVIDIA TLT as an example of, think of it as, so the NVIDIA TLT is the NVIDIA Transfer Learning Toolkit that is prepackaged with ClearML. So once you set up or log in into the account, you'll already have the NVIDIA TLT as one of the examples. Think of it as a good example of how your code should look like in the system, and it will allow us to demonstrate the automation part, right? So we can take a code base that was written by NVIDIA that does training. In our specific example, it's going to be object detection. And we'll use that object detection code base in order to demonstrate how we can automate this process, how we can take a code base that is already tested and executed and is on the system, replicate it, change parameters, send it for execution, end up with a model, and then serve that model using the NVIDIA TRITON. Basically, another command line that allows us to spin a serving engine, and that serving engine, again, will pull automatically the latest model from the system, and will just serve it for us. We'll touch that later. So that's kind of the outline for the next part of the session. Okay, so how do we build those pipelines? First step is creating a job, right? So a pipeline is basically a set of nodes. Each node is a task in the system. You can think of it as an experiment, but everything in the ClearML platform is a task. And a task, you can think of it as a set of configuration that defines the environment itself. So think like Git repository, Python packages, Docker image, etc. It is a set of configurations. So think arguments that you pass to command line, but it's actually more than that. We'll deal with that later. And it also means the outputs. So the outputs is obviously console outputs, but it can be metrics like TensorBoard reported metrics, matplotlibs, or artifacts that you're creating. And so everything is a task. So the first step is, so how do we create the initial tasks in our pipeline? So that amounts to adding the 2 magic lines of code. We'll touch that. And then we'll demonstrate how to remotely execute the code that was created with the system. So again, 2 lines of code. They basically create the job template. Once we have the job template, we can clone it in the UI, send it for execution, then have the agent itself run the job for us. And then we'll move into, so how do we automate this process of cloning, changing parameters, etc. And we'll create an entire pipeline from code, and then we'll launch the pipeline itself. So the thing to remember about pipelines, and generally speaking about ClearML, that everything is a task. So everything can be replicated and modified. So even the pipeline itself is a task, which means that we can build pipelines over pipelines, right? So the pipeline is, you can think of it as building blocks, right? So we have the initial task as 1, 2, 3 building blocks, and then we have a pipeline that encapsulates all those 3 steps, and then we can basically repeat that pipeline and allow us, and we have the ability to change the parameters of the pipeline itself, right? So this really gives us the flexibility to build a very complicated set of automation without actually changing anything in the code, because as you remember, from the code perspective, we didn't actually change anything. We basically just added the 2 lines of code, and that's about it. So this entire infrastructure and that entire pipeline, as part of the ClearML, as used by thousands of organizations throughout the world, basically to do that same thing. And I think that the most valuable thing that ClearML introduced is the ability to create those automation and MLOPS in a very easy way, such that we have full visibility into the process. And this is important. So it's not only about running jobs, it's about the ability for every job to have visibility into what's going on inside the job itself. And that means that every job is kind of an experiment, if you like, in terms of data science, with inputs and outputs and metrics. So we can always report on what we're doing. And this is essential, especially when we are thinking about the automation process. So just think about trying to compare lots of different pipelines. If those pipelines are not reporting something, it'll be very hard to understand what went wrong and what's the difference in the accuracy or the loss or the product of that specific model. Okay, so how does it all work? On the left-hand side, we have the user's resources. So machines, either development machines, so upper left corner, or automation machines. So think of them as the GPU machines running the training itself. It can be CPU machines as well. The idea is these are resources available for automation, as opposed to the development resources, which you can think of them as your own laptop, right? So full control, creating the jobs. And then on the right-hand side, we have the ClearML platform, basically acting as a control plane, right? It controls everything, but it stores very little, right? So the storage itself is obviously metrics and reports, etc. But when we think about data, the data itself can be stored on a totally different storage solution. And we'll get into that later when we talk about the automation and the data creation process. Okay, so with that in mind, let's get started with a few demos. Okay, first step, let's just create an account and check how things work. Okay, so first step is we have to sign up for ClearML. Either go to the website and create an account, it's free, or spin your own ClearML server. You can go into the GitHub page. It's basically Docker Compose up and running. That's it. It is that simple. Once you have a server up and running, you have to log into it, and we have to first obviously install the ClearML package, and secondly, configure the ClearML package. So ClearML stores all the credentials in the ClearML file, so we have to create it only once. Obviously, it can be passed through all this environment, etc. So for full automation, pipelines, etc., this is out of scope for this session. And this session will only talk about the ClearML configuration file. So again, we install the pip package. And now we will just run the ClearML init. It's command line that will be installed as part of the package itself. So let's run the ClearML init. And now we have to copy paste the configuration definition again with the credentials that were created on the ClearML website. So let's go to the ClearML website, create credentials. As you can see, it can be configured to point to your own ClearML server. So right now it's pointing to the community one, the free tier. But if you're spinning your own, you'll basically have your own IP address instead. So once we have that and we press enter, it should be able to verify the credentials. Yeah, we're done. Okay, so now everything that we do, basically we don't have to provide any credentials. It will know our own user, permissions, etc. Next step. Let's start small with creating data. We'll be using that data in a second. So ClearML data is another command line that is installed automatically as part of the ClearML package. And the next step is essentially creating a data set from our own local copy of the data, right? So one way to achieve that is, let's assume that I have my data on my machine and I want to make sure that, first of all, I have a stored copy of it so I don't lose it and it's properly immutable copy. But the other is I want to make sure that when I launch on another machine, my code base, I'll be able to access the data, right? So creating data sets and accessing data sets can be done either with a command line interface, such as the ClearML data, but also programmatically with the Dataset class, right? So right now what we'll do is we'll create a data set. So this is just a very easy data set with only a few files. What I'll do is I'll just sync my current state of the data set. So let's assume that I have a folder with all my files in it. So let's assume like CSV files or Paquet files or whatever. And what I'll do is I'll create a new data set, I'll sync it with the current one, and everything will be uploaded. By default, it's going to be uploaded to the ClearML server. It also supports uploading it to any HTTP server and object storage, so think like S3, Google Storage, Azure Storage, or any shared folder even. Again, the idea is the control plane itself, the ClearML server, is storing a link to the data itself, and the data itself can be stored anywhere. Obviously, if you need to provide credentials, go into the ClearML configuration file and just add your own credentials. Those are stored only on the ClearML configuration file. So even if you're using the community server, those credentials are never passed. And the same goes for running your own server. So we really have to separate here between the metadata and the actual data that is stored here. So again, actual data stored somewhere, again, default ClearML server. So we'll upload everything to the ClearML server. Again, the storage itself is actually smart storage, so it will store the delta changes from the parent version. So if we are constantly increasing the data set, so let's assume that we have like a weekly cron job, pulling data from production, adding more files from the production database. Every time we create a data set and we specify the parent data set, we only store the files that were changed compared to the parent data set. And obviously when we want to collect everything, the ClearML command line interface or the class itself will collect everything and we'll just recreate this entire folder, including subfolders, etc., all the structure inside a remote machine, right? So again, think of it as kind of the easiest way to package everything in an immutable way and have everything logged for us. So, and now obviously let's just sync it. As you can see, the output of that is another line in the user interface, right? So everything is a task in ClearML, even data is a task. And the reasoning is data itself is actually or in a lot of cases, coupled with code that is creating it. So for example, if we go back to the cron job, collecting data from the production database, this is actually a piece of code, and we want to log that piece of code that creates a data set alongside the data set itself. So even the data set itself is kind of a task in the system. And that means we can add tags to that specific task. We can log the exact code that was used in order to create it, but we can also fetch the data that data set is storing for us. obviously it has a specific type that task is obviously a pre-processing data set. And okay, so now we're done with the data, and let's talk about connecting the code itself. So again, connecting the code, we can do two things. Either we add the two magic lines of code, so we import the ClearML package and we initialize the task. This will essentially log the Git repository that we're running, or the Jupyter Notebook if we're running inside the Jupyter Notebook. It will log the arg parser, so every arguments that we're passing. It will automatically log every output that we're doing, so storing models in joblib or TensorFlow or PyTorch. It will log the TensorBoard outputs, the matplotlib outputs. Everything will be logged automatically. The other option is, let's assume that we just want to create a task from an existing code base that we don't have on our own machine. So we can use the ClearML task in order to basically create a task and point it to the correct repository with the correct script to run. We can actually add some arguments to override the default arguments, or specify packages if we think that requirements.txt file in the repository is not updated. Once we have a job in the system, then we can obviously automate and execute it on a remote machine using the agent. So how does it look like from like an actual code example? So let's take one of the code examples that we have. So this is the PyTorch MNIST example. So again, we have some arg parser parsing some input arguments. We have the task in it, again, recording everything for us. So again, it will do a lot of stuff in the background. It will spin another thread that will monitor the entire process. It will also monitor resources, so GPU utilization, CPU utilization, etc. And again, in the last line, we're creating the TensorBoard. So everything that we're reporting to the TensorBoard will be automatically logged by ClearML. We can always extend that with direct interfaces if you want to know more. Just go to the website, documentation, etc. Okay, so once we have that and we can see the experiment in the UI itself, it's all about trying to automate this process, right? So how do we move from seeing the execution itself, so from logging on our development process to automating it? So for that, we need to install the ClearML agent. And the ClearML agent, again, we'll start very simple with the ClearML agent running on bare metal. It can always, in your Kubernetes cluster or your cloud instances, we will not get into that in this session, but it's all there if you go to the documentation and you'll read more about it. So we'll start by just installing the ClearML agent on our machine. Again, pip install ClearML agent, and then we obviously need to configure the ClearML agent. So ClearML agent init. This will, and then we obviously need to copy paste our credentials. Now we already created the credential because we did the ClearML init, so it's using the same configuration file and it extends it. So if you want to learn more about the different configurations that you can use when setting up the agent, go look at the documentation or on the Git repository. You'll have a full link of everything that you can add into the configuration file, controlling caching environments, different packaging solutions, etc. I will not go into that in details today, but what we'll do is we'll just install the agent and spin it. So we just install the agent, so everything is working. Now we can spin it. So the agent can run in two different modes, right? So it can run in Docker mode and it can run in virtual environment mode. The virtual environment mode, think of it as every process or every experiment that the agent will pull from the execution queue. It will set up an environment based on the requirements of that specific experiment, right? So create a new virtual environment. It will install all the packages that the tasks need. Again, those packages are pre-populated automatically when we first executed the task itself, right? So when we're executing the task, when we're calling task in, when we're writing the code, it will automatically pre-populate the task itself with all the different install packages that are needed, including specific versions. So the only thing that the agent needs to do is basically set up the entire thing, clone the code. If this is a Jupyter notebook, it will be converted into Python code. If it's a Git repository, it will clone the Git repository. It will also make sure that it will apply all the uncommitted changes, because we know that we cannot commit all the changes all the time. Otherwise, we'll end up with a very messy Git repository. And it will spin the code for us. If we're working in a Docker mode, that means that this entire process will be happening inside the Docker that we choose. So if we do not specify a Docker, the agent will take the default Docker, which I think is the NVIDIA CUDA Docker, and then everything will be done inside that Docker itself. So cloning the code, creating the virtual environment, inheriting from the virtual environment, from the Python packages that the Docker already contains, everything is done inside the Docker itself. So we can actually reuse Dockers without the need to constantly create them. If you worry about caching or the time that it takes to spin a Docker, everything is cached. Cloning the repository is cached, the virtual environment is cached, everything is cached. So spinning a Docker only takes a few seconds, and you end up with a Docker with your entire code in it, running without us having to worry about how to manage Dockers, creating an artifactory, and constantly packaging them. So again, everything is done for us. So with that in mind, let's take the previous execution that we had. So we were running the PyTorch MNIST example, and we had it in the system. Now let's just cloning in the system and change a few parameters and send it for execution on the agent that we just started. Okay, so let's go into the project. Here's our code, and now we can clone it. Let's give it a name. Obviously, clone of clone of clone is always what we end up with. And now we can go into the configuration tab. So now we have all the different arguments. And now everything is editable, right? So now it's a job template, right? Everything, we can change everything. We have no results. We only have the configurations. So we can change some of the parameters. Let's change, say this one, whatever. And we save it. As you can see, everything is logged. Again, the commits, the specific code base, everything is logged. And now we can enqueue the job for execution, which means we take that job ID and we push it into the execution queue that the agent is listening to, right? So the agent is basically pulling jobs from an execution queue. We can have multiple agents listening to the same queue, pulling one job after the other, and then it will pull the job and start to run it. So think of the queues as a way to abstract the resources in the system. So we can have multiple queues doing different things. So imagine like a single GPU queue, dual GPU queue, on-prem GPU queue, cloud GPU queue, whatever makes sense in your specific scenario, as long as the users understand what they'll be getting, right? And you can always mix and match and have a very dynamic way of attaching and reattaching agents to Dockers, to queues. So now we'll just check the on-prem one, and we'll send it for execution. Obviously, it's on-prem. And now the agent will start to pull the job from the queue, and it will start to run it. So if we click on it, we can see that it's setting up the environment in real time. And in a few seconds, we'll be able to see the entire reporting happening in real time. So now I can actually monitor my performance, my execution, while it's running on a totally different machine. And with that, it will end. And now what we can do is move into the more sophisticated process. So this was all toy examples. They work very nice. Awesome. Now let's move into a more of a real-world example. So the real-world example is basically taking the NVIDIA TLT, connecting it with new data sets, training a new model, and ending up with a serving of that model with an endpoint served by the NVIDIA TRITON model. And the idea here is, again, so the NVIDIA TLT, obviously it's, again, if you log in, it'll be part of your examples project, so it's already pre-baked. But the idea is that you will have the same experience with your own code once it's connected, right? So you can reuse it and automate this process. So now again, let's clone the NVIDIA TLT example. So we'll start by cloning the training process. So there's an entire process here. So we train, we can evaluate, and we can prune the weights, right? So they're more efficient. So the first step is basically cloning the training session. We'll do it from the UI, and then we'll do the same thing from code. And that's kind of the idea here, right? To automate this process. So again, we start by cloning it manually, sending it for execution. Same process, right? Cloning, change the parameters if we need to, and then just sending it for execution. And now our agent will pull the job and start to execute it. Wonderful. Okay. And now, while that is running in the background, we can talk about how to automate the process, the creation process. How do we automate this process, right? So now what we did was we manually had to click and move from one to the other. How do we automate this process? So again, we have 3 steps in this specific example. So we had the creation of the data. Let's put that aside for a second. We have the training, the evaluation, and the pruning process. So let's try to automate these processes so later we'll have a single task, a single pipeline that we can basically launch automatically, and that pipeline will be in charge of running through all those steps, right? So we create a new pipeline. So everything is done from code. So the pipeline is created from code. Later, we can see how this pipeline looks in the UI, but the code itself, but the pipeline itself is created from code. So we create a pipeline, we add steps. So each step is a task that already exists in the system because we tested it. And we can basically say for each step, run it after a specific parent was executed. And we can also modify the code itself, right? So we can say, change the input of one task based on the output of another task, right? That's how we pipe the inputs into the output. So over here, we have the training, the evaluation, and the pruning. Obviously, the evaluation and the pruning they need to use the model that the train process created. And once we have that, we can start the process itself. So we start the pipeline, and we basically end up for the pipeline to end. That entire code base is also a task in the system, right? So that entire pipeline is a task in the system. So now we can replicate that exact same task in the system and repeat the pipeline by cloning the pipeline task and sending that pipeline and executing that pipeline automatically. So, right, so we moved from writing our own pipeline or running our own pipelines manually through the UI to writing code that does that to automating the pipelines as processes in the system itself. And obviously, we can repeat this entire thing and queue the pipeline. So now we can actually start to automate the automation, right? So what we do here is we actually get the pipeline task, we clone it, and we send it for execution, right? So we started manual, pipeline, automation of pipelines. And with that, I will leave you with a few takeaways. So what have we seen? We've seen how to take any piece of code with 2 lines of code and connect it with the system. We saw how to create or connect any machine to our cluster using the ClearML agent, right? So we can automate these processes. We saw how to automate the executions of tasks from the UI, and then we saw how to write pipelines from code that will run the automations. And then at the end, we saw how to automate the automation itself. Obviously, what we need now is how to serve the model itself. And just look at that. So now what I'll do, I'll go into the command line and I'll write ClearML serving, and I'll just add the project that it will be monitoring, and I'll press enter. And that's it. This is the only thing that I need to do. It will do all the rest for me. It will spin a Docker with NVIDIA Triton. It will monitor this project for me, and every time a new model will appear and will be published in that specific project, it will be automatically piped to Triton, and Triton will serve it for me. It is that simple, right? So we could actually move from writing code to full automation with very little effort. So to learn more, go to our website and to our GitHub. Check us out on our Slack channel. Don't be afraid to ask questions. You can also ask questions on our Stack Overflow. Just add ClearML tag, and don't forget to star us and check out the Twitter.